Okay, so please excuse the audio issues that we just had, but welcome back. Our next presenter was previously the director for the Natural Sciences program at UNM for 10 years. He is now one of the educators at the Bradbury Science Museum and specializes in electronics, geology, volcanology, and the study of the best little monsoon in the U.S. I present to you the one, the only, Mr. Mel Strong.
Thank you very much, Katie. And thank you for Katie. She has put together this whole Earth Week event. So not just the talks you're seeing today, but all the things that have been going on this week. I think she's been working on this for, months, it seems like. The Earth Week page that's up on the internal site and the external site, that's all Katie. So I'm going to ruin everybody's good time by showing you this map of our current situation. So this is what's called the Drought Monitor. And this is a map that comes out every week, and this one was just released to the public today. And this is a map showing the rather dire situation that we're in terms of drought. And the colors that you see here correspond to everywhere from abnormally dry to moderate drought, severe drought, extreme drought, and exceptional drought. So you can see a big chunk of New Mexico is in this exceptional. I mean, we are beyond extreme, people, according to this diagram. But you also can see that this drought is not just us, right? It's the whole western U.S. is kind of in trouble here. And in fact, there's been a couple of stories just this last week about this situation. So the AP ran a story a few days ago where, Lake Mead, which is in next to Las Vegas, Lake Mead is getting so low that they're predicting they're going to have to declare the very first, basically, water emergency, which is going to ration water coming from the Colorado to everybody downstream. And then also CNN had a story that says, as a mega drought persists, new projections show a key Colorado River reservoir could sink to a record low. So same story about the same thing, but CNN, that's an inappropriate use of the word mega drought. We are not in a mega drought. If we have enough time, I'll get to what a mega drought is. But we're not in good shape. And so after having a very dry winter and a very lousy monsoon last year, the question that people are asking is, well, is our monsoon that's coming up, is it going to get us out of this hole that we're in? Or are we in some kind of pattern where we're going to expect another dry one? And so my goal today is to try to lay out how the monsoon actually functions. Why does it exist? Why is it here in the first place? Can we predict what's going to happen in the future? So that's kind of where we're going with this. And where I want to start is actually not at the monsoon, but I want you to look at some of these graphs that were made of average monthly rainfall for different locations in the United States. So for example, if I go to San Francisco and I just average how much rain do they normally get in a month, from January, February on into summer, what I see is we have a wet winter, goes into a dry summer, goes back into a wet winter, okay? If I go east a little bit, anywhere out sort of in the middle of the country, what I see is almost the exact opposite. I see dry winters and I see wet summers. Now, if I go to the northeast or if I go to the southeast, it's kind of flat, right? There's not really these types of patterns. So here's what I want you to do. I want you to visualize in your head a graph. What would it look like if we did this type of graph for New Mexico? Let's say Los Alamos. What do you expect it to look like? So we get snow most years. We get monsoon most years. Is that like the same amount? How is that balanced? So you got your graph in your head? Good. So there's the graph for Los Alamos. And so what I've done here is I've shaded July, August, September. Those are our 3 monsoon months in red. And if you just kind of eyeball this, you'll notice that the amount of rain that falls in this blob here in the summers, more or less pretty close to the rest of all the blue bars for the rest of the year, right? And we'd also see there's this very significant jump right here from our dry spring to our wetter July, right? Okay, well, I can make more of these graphs around the state. And so it turns out as I go further west and further south, I start to see an exaggeration of this really dry spring with a really wet summer. In fact, we call this the monsoon signature in graphs like this. So, for example, here's one. So you can see that the jump from the dry spring to the wet summer is much greater than what we have here in Los Alamos. Well, if I continue to make these graphs, and let's say I go further south still, and go down here into Mexico, I find that actually this effect amplifies even further. And these little ones are hard to see, but for example, I made one here for Hermosillo. Look how giant this pulse of moisture is in the summer compared to not only the rest of the year, but also this extremely dry spring. Now, another way that we can kind of get at this is something we call the Monsoon Index, which means if I added up July and August and September, if I added those 3 together and divided it by the annual precipitation, in other words, what percentage of rain falls during the monsoon, right? What percentage of our annual rain falls in the monsoon? I could get a number and I could map that number. And if I do, I get a map that looks like this. So in other words, if you're living behind the 40 line, that means that 40% of your annual rain falls during the monsoon season. 45, 50, you'll notice as we go further down here, the numbers are increasing. So this map tells us a couple things. Number one, compared to the rest of the country, we have the biggest, our state is more influenced by this monsoon system than anybody else in the union. But also, as I go further south, I start to see, oh wait, this is really actually a Mexican phenomenon. In fact, I can also not just graph the monsoon index, but I could also look at actual amounts of rain that fall. And this is a very busy graph, but all I want to show you here are these contours. What they did is they have contoured the average precipitation during a month in July, right? So just 1 month of precipitation. What do you normally expect? And it's all in millimeters here, but the key is down here in this part of northwestern Mexico, they're getting upwards of 9 inches of rain, okay? Whereas up here, we might get 2. Okay, so no matter how you measure it, what we call the monsoon is really a Mexican phenomenon. And in fact, depending on when you live in history of monsoon literature, you'll hear it called different things. So if you look at papers that were written 50 or so years ago, they call it the Mexican monsoon. And then you'll see papers even before that call it the Arizona monsoon. And you think, well, that's weird. Why would you call it here's Arizona. There's just a little bit down here. Why would they call it the Arizona monsoon? And then you realize, oh, that's right. University of Arizona is in here. There was researchers there, so they just decided to call it the Arizona monsoon. Well, the name that we actually call it today is called the North American Monsoon System. I'm missing the system here. Or NAMS, which is a terrible acronym. But that's the official name for this system that we're talking about. So before we go any further, we got to talk about what do we even mean by monsoon? This is a word that's abused a lot in everyday language. People talk about there's monsoons today, but they're not tomorrow, or we had a monsoon earlier, or the monsoons are coming, that kind of thing. But a monsoon is actually a seasonal reversal of wind direction. It just so happens that in most parts of the world, when you have a seasonal reversal of wind direction, you also get a big change in precipitation. And so if we, for example, go over and look at some of our friends on the other side of the world. So what we're looking at here, I'm going to be using this 3D data viewer, and what we're looking at is weather data that's plotted on a globe. And the colors right now represent how much water vapor is in the atmosphere, so humidity, okay? So the blue colors are the more humid air, the brown colors are the drier air. So here's India right now, and the part that you may or may not be able to tell, depending on how big your screen is and how fast your internets are, is that it's also animating winds. So I have picked a random day in the winter, and on this random day in the winter, I'm looking at what's going on in India. And what I notice is that the wind is coming down off the continent and out over the ocean, right? So it's blowing from the northeast, and it's very, very dry, right? So this is very dry air up here in the continent. Now, if I then pick a random day in the summer, I'll see that actually the situation has reversed itself. So now the wind has completely reversed, and now that really humid air is now all over the continent. So this is what a true monsoon is. Now let's compare that to what we get. So now if I go to, say, a day from last week, which day do you ask? The windy one. You know, the windy one. Most days in the spring look like this. We are dry. You can see the brown there. And if you can see the animated wind, what you see is coming out of the west, headed towards the east. These are the westerlies. And we've been getting them day after day after day after day this time of year. Okay, well, if I compare that, say, to a random day in the monsoon, it looks something like this. Okay, so here you can see that, so again, if you kind of make out where New Mexico is, we're kind of right in here. Notice that the wind is, on this particular day, is coming from the southeast. Notice that humid air is coming in, invading our state. Not really a true reversal, but also, let me jump forward a couple days. I want you to notice if that wind direction changes. So, okay, so I'm going to one day forward, it's coming a little bit more from the south. Another day forward, directly south. Now a little bit from the southwest. Okay, now it's more west. So, in a matter of a few days, that wind direction has changed a little bit, but in both instances, it's bringing up moisture. Now, is that a true monsoon? A monsoon purist would say no. What we saw in India, that direct reversal, that's the real thing. Ours is pretty wimpy, but it's the only one we got, and we're pretty proud of it. So we're going to call it a monsoon anyway. Now, the key to the monsoon, as we're going to find out, is that if I look at the sea surface temperatures, so here's a sea surface temperature map for around this time of year. The Pacific Ocean is a pretty cold ocean. So right along the coast here, there's a lot of cold water that's welling up from below. By comparison, the ocean down here is a lot warmer. And then when we get to the summer, we see that actually both the Gulf of California and the Gulf of Mexico are very, very warm bodies of water. So when we get winds that come off the Pacific, the westerlies, they're not going to bring us much moisture because that's a cold ocean. We need wind to come off of a warm ocean. So we need wind to come from either of these two bodies of water. All right, so we can't go any further until we talk about humidity. And humidity is a very, very, very confusing subject. And the reason it's so confusing is because it's commonly completely misreported and misunderstood by the public. So first of all, Most of the gas in our atmosphere is nitrogen, and then number 2 is oxygen, right? At the very most, you can have 4% water. And that, in order to get that, you got to be in like an equatorial zone. The amount of water in the air is somewhere between 0 and 4% of the total gases. However, when you have heard humidity being reported, you've heard something called relative humidity, which is on a scale between 0 to 100%. And relative humidity actually doesn't tell you how much water is in the air. And this is shocking to most people. But the relative humidity can go up and down, and it doesn't have anything to do with how much actual water is in the air. Don't have time to go into why that is right now, but pretend you've never heard of relative humidity, okay? Because I'm going to introduce another way, a better way to report humidity. So there is a super important, I'm going to call it a law in meteorology, one of the basic tenets of meteorology, which is, there's always some water vapor around, but there's a limit as to how much water vapor you could actually put in the air. And that limit is controlled by the temperature. So in general, warmer air is allowed to have more water vapor than colder air. Okay? So there's some implications to this. Number one, that means if we have warm air, it could be humid or it could be dry. Without more information, we don't know. But cold air is always dry air. The colder the air, the less water can exist in the vapor state. If I have a blob of air and I start to cool it, at some point, water vapor is going to have to condense and remove itself from the air. And so, you may be familiar with this because if this happens overnight, we get these blobs of water on the grass, which we call dew. And if I'm showing this picture to most New Mexican audiences, I have to point out this is what dew looks like, because this is something that we get maybe a dozen nights a year. Okay, it's not very common here because our air is so dry. But if you can imagine a night where you go to bed, there's no water on the grass, but it starts to cool, the temperature's cooling, you're going out and you're checking the grass, and all of a sudden, maybe it's 3 a.m, and you start to see these little drops of water start to occur on the grass. At that instant in time, we have hit what's called the dew point temperature. And if I cool it further, my drops just get bigger as I pull more and more water out of the air. Okay, so imagine I got 2 boxes of air. One has a little bit of water in it, one has a lot of water in it, in the vapor state. And I'm going to cool these down, right? They're at 80 degrees, but I'm going to start cooling them. And what I'm going to notice here is that I'm going to start to get condensation at 40 degrees. So I would say that the dew point temperature for this box of air is 40 degrees. This box of air, I've got more water. I'm going to hit the condensation point sooner. I don't have to cool it down as much until water starts to come out of the air. So I would notice maybe the condensation starts at 55. So I would say that the dew point temperature is 55. Well, in this roundabout way, we can use the dew point temperature to figure out how much humidity is in the air. So we actually drop the word temperature and we just say the dew point. Okay, now if that's a little abstract, I don't blame you. All you really have to know here to understand what I'm going to do next is if I have higher dew point, I've got more water vapor in the air. If I have lower dew point, I have less water vapor in the air. So for example, today, the dew point here in Los Alamos is about 18 Fahrenheit. Houston is about 40. Miami is like 72, so I mean they can get dew by just dropping down the room temperature. Go to Antarctica, minus 95, right? You've got to really chill that air to get any moisture out of it because it's so dry. Okay, so the reason we talk about dew point is because when we get into monsoon season, dew point is the main part of the game that we're paying attention to. Okay, so here are some graphs that the National Weather Service has made for past monsoon seasons, and there's a lot going on here. I'm just going to look at the blue line, just the blue line. So This is a graph of dew point temperature. So what we just said is that when the dew point is higher, you have more water vapor in the air. Okay? And dew point's lower, less water vapor in the air. That's all you got to know. Okay, so here we are in early June, right here. And notice that we have some humid air, then it goes dry. Then it goes humid, then it goes dry. Humid, dry, humid, dry. But it's starting to bounce up and up and up and up. And then it stays relatively high, a few little dips here, pretty big dip there, and then bounces, and starts to head back down. And then our jumps up and down start to get more extreme. Okay, so this is 2017. Let's say I look at another year. Same but different. So 2016, I see these wild jumps here in the spring, and then it starts, in this case, it fell off in the summer, bounces back up, reaches pretty high point up in here, and then starts to come back down again. If I were to average the dew point that's taken every day over, say, 30 years, or more than 30 years, and I would plot that, I would get this red line. Actually, this one's 75 years. So on average, the dew point starts out in June around 30 degrees. It grows and grows and grows. But remember, we're looking at an artifact of math here. We've averaged all the giant wiggles over all those years to get this relatively smooth curve. Well, you'll notice there's this green line here, and that green line is 47 degrees. So one definition of when does the monsoon actually start is that the National Weather Service somewhat arbitrarily picked that if you have 3 consecutive days where the dew point is over 47 degrees, we're going to say that the monsoon has started, right? So doesn't even mean it's raining. That's just a somewhat arbitrary decision that was made. In Tucson, they do something similar, but they use 54 degrees because they have more humid air than we do during the monsoon. So, so 3 consecutive days after this point takes you to about right here, which is July 11th. So July 11th is often given as the start date, the average start date for the monsoon. But it's kind of, it's just statistical average. It doesn't really mean a whole lot. But if you notice, if we don't start getting rain right around in here, the newspapers are going to start running headlines about, is the monsoon going to come, right? Because everybody's expecting this is the average start date. But a lot of crazy things can happen. So for example, 2016, notice what happens. So we go for this dry air, and we're in the middle of June, and it's bumping up, and it's bumping up, and there's that 47-degree line. And look at that. Day 1, day 2, day 3. We just did 3 consecutive days where the dew point's above 47. Everybody's excited. The monsoon has started, and it started early. And if you go back and look at so this is near the end of June. If you go back and you look at the headlines back then, you'll see that everybody's excited that the monsoon is here, it's early. But then notice what happens. July gets here, and the dew point takes a big dive. And we end up having an almost entirely dry month of July, right? We don't actually bounce back. We just hit normal here, and then we bounce back down, then we hit normal again, and we're finally kind of out of the woods by the time August gets here, right? So what we want to do today is explain what on earth is happening to cause things like this crazy up and down, right? And in general, why does this happen at all? Like, why does the dew point go up in the summer in the first place? Okay, so that's kind of where we're headed with all this. And what I'm going to do is I'm going to have a look at the world today. Okay, so this is Google Earth clouds, the cloud layer. These are the current clouds as projected on Google Earth. And these are not all the clouds, because what's being projected here is actually the very, very tall clouds. using infrared satellites, it's like it's filtering out the low-level clouds. So every cloud you see here is really tall up into the upper atmosphere. Okay, so if I look around here, there's a lot going on, but one of the things I want to point out is that, do you notice, let's just say right around in here, I see this kind of narrow band of these white clusters of storms, kind of right around the equator, right? And we kind of lose it over here today. So each one of these white blobs, if you were to look at it in detail, is a gigantic cluster of thunderstorms, bigger than anything we ever get here on the continent, right? We're talking about thunderstorm cells larger than the state of New Mexico, drop a couple feet of rain every day, right? This is going on every day. Why is it going on? Because it turns out this is the warmest part of the Earth, and air is rising. And when air rises, if it continues to rise high enough, it will expand, cool, condense, and start to make rain. We'll talk more about that a little bit later. Well, that air that goes up runs into a problem, because the problem is that this air can only rise to a certain distance, and then it runs into what we call the stratosphere. The stratosphere is the part of the atmosphere where it actually gets warmer with height, and that's due to the ozone layer that's up here. But what that means for our thunderstorms is that the air rising hits a wall and it can't go any further. So it has to expand out sideways. So we can kind of see this on Earth. This is not one of those giant thunderstorms at the equator. This is just one on the land, a little one. But you notice what's happening up here. You can see this is the part we call the anvil, and it's spreading out. That's the air getting stuck underneath the stratosphere, and it's spreading outwards. Well, this is happening all along the equator where we saw those big clusters of thunderstorms. Well, what happens is that air has to go somewhere, so it goes north and south. So here is a highly, highly exaggerated view of this. This is all happening within a speck of the fuzz down here. I just exaggerated this to make a point. Our thunderstorm, the airs from our thunderstorm, our big thunderstorms near the equator, it rises, it hits the stratosphere, has nowhere to go, can't go up any further, so it starts to go north and starts to go south. It doesn't have any other options. As it starts to travel, it continues to cool. I mean, it's pretty cold already, because this is maybe like 80,000 feet where this is happening around on the equator. And as it's cooling, it's very slowly starting to sink, and it turns out it comes down right around 30 degrees latitude. Well, when the air is coming down over your head, the air around you is being squashed. So in other words, you can imagine like a big pile of air being shoved on top of your head. And the air pressure at the surface goes up a little bit. And we call that a high pressure, a center of high pressure. And that does a few things. For one thing is it kills our clouds. Sinking air kills clouds for a couple reasons. But the main reason is that it warms the air above our heads. It's compressional warming. We need our little parcel of air to rise to make a thunderstorm. It can't rise if the air above it is also warm. It does some other unfavorable things. It makes temperature inversions. It holds pollution to the surface, other kinds of things. But imagine, if you will, what would happen if the Earth was all water? What if we lived on a water planet? Okay, there's no continents. If that happened, then what we'd expect is we have a band of thunderstorms, and we have rising air that gives you low pressure, and then that air falls back down to about 30 degrees north and south, and you have a band of high pressure. We call these bands of high pressure subtropical highs. So you'd have these nice bands that go all the way around the Earth. It turns out, though, when you have continents, it messes this pattern up. Now, in the northern hemisphere, wind moves clockwise around high pressure. It's the opposite in the southern hemisphere. We don't care about them. We're in the northern hemisphere. So we have clockwise rotation around all of the highs in our band of subtropical high. All of these little arrows kind of combine together to form a band of wind that we call the Westerlies. And below, south of the highs, we have a band of wind that we call the Easterlies. So if I throw continents into this, then it kind of breaks up this pattern. And this is just a diagram out of a textbook. What they're showing here is they're coloring the subtropical highs yellow. So they're showing it here, and they're showing it over here, and there's this continent right in the way that kind of breaks it up, right? So we can actually see that today. Go back here. Okay, so now what I'm looking at, the colors are now something different. I'm looking at air pressure. And this is a random day I've picked. And what I can see here is, so here's the United States. Out here, there's this big swirling pattern of wind. That's the Pacific subtropical high. This is a big blob of air that's sinking down from the upper atmosphere, came from the equator, came up through those thunderstorms, traveled all the way here, has sunk back down, making clockwise winds that go around it. I can go over here, I can see, here's another one. And this little light yellow color means high pressure in this case. So there's one over here in this ocean basin. In fact, they end up in all the ocean basins. So for example, if we go into the southern hemisphere, we'll find them, except in this case, it's spinning the opposite direction. These are subtropical highs. Now, what we got to get into is how all this is going to change, okay? So we have these big storms near the equator, air going up. We have air coming down, forming these big high pressure centers where there's no clouds, but it's going to change its position over time. So if we look at just how much sun is hitting the Earth, and we animate that, it would look like this, right? So we've got a band, that, the red represents this band of more intense sunlight, and it traverses up and down across the Earth. If you were to do this, but instead of looking at sunlight, look at the warmest temperatures, it looks a little different because it turns out the land warms up much faster than the ocean. So what we're looking at here, the dark red, these are the locations of the warmest parts of the Earth, right? And you see it's not nearly as symmetrical as we just saw with the sunlight. So year after year, there's this band of the most intensely warm place on Earth migrating north, coming back south, migrating north, coming back south. Well, one of the things that's going to do is it's going to change the locations of these things that we're talking about. So I have this little kind of a, let's see here. I got this little animation, okay? It's a little middle schoolish, but it's pretty good. And what's plotted on here is this purple line, and the purple line represents the part of the Earth that's the warmest at this particular time. This is where all those big thunderstorms are going to form. And you notice it's not straight, right? It's got these curves because the continents and the oceans are almost never the same temperature. Also, you see these highs. There's some up here, there's some down here. These are the subtropical highs. That's where the air is coming back down. So it's rising along this purple line. It's coming down where these highs are. And it's shown here in profile view. And this is called a Hadley Cell. This is the main circulation cell in the Earth, okay? Okay, we are now in January, and I'm going to progressively move forward in time. And as I do so, you'll notice that this purple line, the line of the warmest temperatures, is moving north, right? As I do this, also, these things are moving north with them. So if I move further and further into our summer, I notice that these two high pressure centers, they were down here. Let me go back. So in the winter, they're further south, they're closer to us, to the United States, and they're weaker. As I move into the summer, they get stronger, but they move further north, and they kind of pull apart from the United States. This is an important part of our story. So in fact, what we're going to do is we're going to zoom in on this little piece right here, right in here. We're going to look at what happens when these two high pressure centers move like they're showing in this little animation. Okay, so before we do that, we got to talk a little bit about air pressure. So air pressure can be recorded in a number of different ways, but one way that we often record it or report it is something called millibars. So around the ocean, sea level, there's about 1,000 millibars of air pressure. You get out in space, you got 0 millibars of air pressure. So if I had 500, that would mean that half of my air is above 500 and half of my air is below 500 in terms of mass. However, Earth has gravity and it tries to pull the atmosphere close to its surface. So if I was to make a more realistic guess as to where 500 would be with reference to 1,000 and 0, it's actually kind of closer to the ground. So most of the air is being hugged to the surface by gravity. Now, let's say I warm up a portion of this atmosphere and I cool a portion of this atmosphere. What I notice is going to happen is that the part that's warmer expands and the part that's cooler retracts. So if I were, say, to make a map, an elevation map of where that 500 millibar surface is, I could make something that looks like a topographic map, except it's representing this surface in the sky. Okay, so getting a little abstract, but that's okay. We're going to call this the 500 millibar height map. And here's what one of these things looks like. So it doesn't matter if you can read the numbers, but these numbers are higher and they get lower going down here. What I'm looking at is I'm looking at the average height of what we call the 700 millibar, so that's right around 10,000 feet in the elevation in terms of the air pressure, height map. So here it's higher, here it's lower. And just to relate that to what we've been talking about, this is the warm air, this is the cold air. So this warm air here, that's the blob that's coming down from the upper atmosphere. This is air that was coming up from the equator, has traveled over, and now it's falling down on our heads, right? That's what this is, okay? And so we're kind of looking, remember, that's what this high pressure here, that's this high pressure here. That's what this is. Okay, so we're going to start in January, and the part that's over here we call the Pacific subtropical high. The part that's over here we call the Azores High or the Bermuda High. Now, the reason we're going through all these complicated looking maps is this is going to dictate which way the winds blow. The winds are going to blow parallel to these contour lines. They're going to go clockwise around this high. They're going to go counterclockwise around a low. So in January, again, this is averaged over a whole month, what we see is we've got, in our neck of the woods, wind coming out of the west, westerlies, right? We said this earlier. Down here in southern Mexico, we can see that they're on the nose of this high, and they're getting this wind that's kind of reversing, right? Okay, so we're going to keep our eye on what happens to this as time goes on here. So move to February. Okay, doesn't look that different. We're still in the westerlies. March, we're still in the westerlies. April, we're still in the westerlies. We're getting a little bit of a dip here, and our high pressure is starting to kind of move a little bit to the north. Now, May, we're starting to get, May is pretty warm for us. We're getting a dip here due to some what we call a thermal low. Here comes the warmest of the warm blob of air that we're talking about here. And you'll notice that this part of Mexico is now getting wind coming out of the east. But if you're over here, you have wind coming out of the west. If you're down here, you have wind coming out of the east, right? So those are coming opposite directions. Early June, okay? So we can see that we're still in the westerlies, but it's dipping down. And remember, we also said that the water here in the Gulf of California is warmer than the water in the Pacific. So if we can get some moisture out of here, our dew point will go up. And if you remember my dew point graphs, all the crazy ups and downs in Junes, well, this is part of where it can come from. Late June, now our high here is moved further north, and so you can see what's going to happen. We're getting this wind pattern where it's bringing in humid air off the Gulf of Mexico, bringing it in right now over Texas. Then it gets caught in the westerlies and loops back out over the continent. So now, early July. This is when our monsoon starts. Our high pressure has now moved so far to the north that the nose of it, this ridge, is starting to be right in line with New Mexico. And we finally have a path where we can get moisture that comes up from the Gulf of Mexico, can come up through basically Rio Grande Valley, and then up into southern part of the state. This is the beginning of our monsoon season. We can also get moisture coming from Gulf of California. Late July, this pattern is same but stronger. Early August, same but pretty much the same. What we're going to see now is this is as far north as this high pressure gets, and then this whole system is going to start sliding back down to the south. So just to connect the dots here, we are looking at, again, this progression, right? We get into the summer, the thunderstorms are moving further north, those high pressure centers are also moving further north, and they're moving further away from us as well, but that is changing the wind direction for us, and ultimately the moisture source. Okay, so then we get into late August, it starts to sink back down. Early September, this is near the end of the monsoon, so we still have a path to get some moist air here, but by late September, it gets shut out. And then we get here into, say, the average. Again, remember, red is the average. On average, our monsoon ends right here about somewhere in the middle of September. And then just to close out our story, late October, back in the westerlies, wind, coming out of the west. That's our story. Okay, so that's the general circulation pattern. However, if you lived here long enough, you know that every monsoon is not the same. We get dry years, we get wet years. We also get periods where we see more moisture, like for a few days it'll rain like crazy amounts, and then we'll have a few days where nothing happens. So we call these periods monsoon bursts and monsoon breaks. So monsoon burst is where you have a dew point that's higher than average. A monsoon break is where you have a dew point that's lower than average. And the number one thing that controls this is something that we tend to call the four corners high. So there's a high pressure, besides the high pressures we were just talking about over here, there's a high pressure that hangs out over the continent. And exactly where that hangs out is really going to control how much rain we see. So we talked about how high pressure makes for very dry air. What if it was over here? Okay, so imagine it's the monsoon season for us, but we have this high pressure sitting here. Wind goes clockwise around a high, and as it goes clockwise, it drags this pretty dry, cold air off the Pacific and brings it down to north. That's not great for us. If I move it here, where the high is right almost on the four corners, that's even worse, because the closer we are to this high, the more it's going to shut down our rain. So it can do two things. It can bring in dry air. It can also prevent air from rising, which is what produces clear skies. Here's the worst case scenario. What if it hangs out right here? So this is, if it's doing this, we're not only not getting rain, we're probably not getting any clouds. And the thing about this four corners high is it can hang out in places for days and days at a time. And this is what happens when we see these extended periods where we get no rain. But what if we put it over here? I just moved it a little bit to the east. That pinwheel is doing what now? right? It can pick up moisture from the Gulf of Mexico and it brings it right into the state. That's a good thing. This is a monsoon burst. And even better is if we had a low, like a thermal low or something over here, this one's going counterclockwise, it can bring in moisture from the Gulf of California. This one can bring in moisture from the Gulf of Mexico. This is like best possible scenario for us. Doesn't happen very often. So, the other thing that can happen, besides our monsoon bursts, are something that, let me go here, get to my, okay. So, when it gets to the summer, we start hearing about hurricanes. But we only hear about hurricanes if they are headed to the United States. But there's a lot of them out there that you never hear about. Tropical storms, tropical depressions, all of this. And there's a lot of them in the Pacific Ocean that we just never hear about here. So here's some. This is a day during the summer, our monsoon season, and we can see that we have several of these pretty well-developed tropical storms. I don't know if they're hurricanes or depressions or what they are. I'm going to go forward a couple days. Now look at this one that's coming up to the Gulf of California, right there, okay? Now, it's going to go past. It's not going to go in it. It's going to go past like that. This happens sometimes. And when this happens, this sets up something that we call the Gulf surge. And a surge of moisture comes up the Gulf and dumps into Arizona. And then eventually gets carried over to New Mexico. So, this, I know this is not easy to read, but what they're showing here are isochrons of a front of moisture from a Gulf surge event. So a tropical storm has wandered by, and it sets up a pulse of moisture that here's a day, next day, next day, and then the next day. Finally, it gets up and gets into Arizona and comes over to New Mexico. So if this happens, we sometimes see an increase in our moisture during the monsoon. We call these Gulf surge events. So here's why it's hard to predict what's going to happen in the monsoon season. To start with, in case you did not know this, weather cannot be accurately predicted beyond about 5 days. Maybe 10 days if you're super, super lucky. That will never change. That will never change because there's too many degrees of freedom. There's too much chaos in the atmosphere. Doesn't matter how big our computer is, doesn't matter how many weather satellites we have, this is never going to change, okay? So, how do you predict climate? It's a different way. You're looking at how the boundaries of the system are going to change over time. This is kind of the same idea with the monsoon. We'll never be able to predict from today if it's going to rain on July 15th. What we're going to try to do is say, well, how is this monsoon going to be compared to years in the past? As we've seen, that Four Corners High, exactly where that is going to play a giant role in what's going to happen. Also, we have no time to get into this, but people have noticed that there are different regions of the sea that change temperature slowly over time. And people have noticed that sometimes you can correlate regions of the sea that get warmer for a few years or decades even, and then they get cooler for a few years and decades. And that has a weak correlation to what happens to our monsoon. We're not doing that, but there are National Weather Service people who are looking into those correlations to make a prediction. And there's also correlations based on what happened in the previous winter. And this one's a lot easier to understand. So if I, for example, look at some forming thunderstorms. We don't have a thunderstorm here yet, but what we have building cumulus clouds. Underneath each one of these building cumulus clouds is a plume of rising warm air. If we want this to be a successful thunderstorm to actually make precipitation, we need our little plume of warm air to rise as high as it possibly can. And the best way to do that, one of the best ways to do that, is to make the temperature down here where it starts as warm as possible. So mountains are a great place to start a thunderstorm because it's like having this warm object up in the cold atmosphere. The mountain warms up in the sunshine, the air does not. And here we have a plume of warm air rising up from the Sandias, forming this thunderstorm. Actually, it doesn't look like it's making rain yet, but it might. So, what if we had a spring that had a lot of snow? We have a really high snowpack. By the time summer rolls around, the soil moisture here, the snow's gone, but the soil moisture here is pretty high. That means that when the sun comes out, the air right above the mountain doesn't warm up as much as it could because it's being cooled by evaporation from the soil. But what if we had a dry winter, like the one we just had? That means the snowpack is very little. That means the soil by the time July rolls around is very dry. That means that when the mountain's in the sun, it's going to warm up faster. That might mean we're more likely to make thunderstorms. So that's one possible prediction. But we have one final complication, which is how is climate change affecting any of this? And what I'm going to do is I'm going to show you a variation of a map that we've seen before when we were drawing little arrows showing you the direction of the winds. This is what's called a 500 millibar height map. And what we're looking at, it's similar to what we saw before, it's just colored. What I want you to notice is two things as we go on here. This is our Four Corners High. The darker the red, the stronger it is. And also these waves up in here. This is the cold air that's up here in the north. Okay, so let me just let this play a little bit. This is the average amount of rain that we got for July plus August plus September. So in other words, this is how successful our monsoon season was. Okay, so let me pause it right there. 2003, terrible monsoon year, terrible. So these maps that I'm making are averaged over the whole monsoon season. What we see is, man, that Four Corners High is dead center right on top of us, right? Terrible monsoon season. Okay. Now let's go forward a few more years. Oh, look at this one, 2006. That Four Corners High would be somewhere over here. Remember we said that makes a monsoon burst. You get that clockwise rotation, drags that moisture out of the Gulf. Record year for monsoon. Okay, let's keep going here a little bit. Okay, 2012, pretty lousy year. Look where that high is. 2013, pretty good. 14, the high's not very strong. 2015, it's getting stronger. And then notice what happens in these last couple years. Okay, I don't know if you're noticing this, but this red is getting darker because this Four Corners High is getting stronger. And stronger still, 2019, pretty lousy year, pretty strong high, right in the wrong place for us. 2020, last year, here's our lousy last year monsoon. Look what happened. We have this really strong high pressure right over us. So here's the worrisome thing. The worrisome thing is that people have speculated, whoops, that's, you don't want to see ugly me there. Okay, people have speculated that as we warm the planet, we are causing that Four Corners High to get shoved over more to where we are. So when you hear about global warming, it's a little bit of a misnomer. If the world has gotten warmer by 2 degrees C, that doesn't mean it all got warmer by 2 degrees C. That's just a mathematical average. What has really happened is that there's big chunks of the Earth where it hasn't changed at all, but look where most of the warming is occurring. Northern Hemisphere over the continents. As we do that, that is shifting, or could be shifting, the Four Corners High further to the west and further south to be right over where we are. And if that's the case, that is a huge bummer. However, just in case you're running out of things to worry about, there's also a natural pattern that can happen. If we look at the last 100 years of monsoons, so every one of these dots, here's lousy last year, pretty lousy year before, okay year before that, right? And then we see it's a lot of up and down and up and down. But we also see that these blue dots, that's the long-term average. Look what happened in the 1950s. We had what's called the 1950s drought, where we had dry monsoon year after year after year after year after year. This is a really bad drought. This is a drought that actually is comparable to the Dust Bowl drought, except it happened further south. And this is probably not caused by humans whatsoever, right? So let's end on this. The National Weather Service currently has this outlook for the monsoon season. They would really hate it to know that I'm showing this to anybody in the public because it's so far out, has very low skill. One of their models is saying that the white is average, the brown is drier than average. This model has been consistent the last 5 months. Another one of their models just came out that said actually monsoon is going to be average or green wetter than average. So when we get to June, National Weather Service actually releases a report that tries to forecast the monsoon activity. They're not going to do it now because we're months away and the skill of these forecasts is very, very poor. So you may know that there is no wagering allowed at the lab, and the reason is because if you ever wager or model results, you're going to probably lose every time. So I'm going to leave it at that, and let me see if I have questions. I don't know if I do. Let me scroll here. Doesn't look like I have any. Okay. Oh, okay. So we are actually recording both of these lectures, and we'll post them on the Bradbury's YouTube site. So that will be there. Where can we see some of these interactive maps? So this site that I keep showing you, this thing, that's earth.knowlschool.net. And I don't know if I can zoom in to show you that. Let's see, can I do this? No, I can't do that. It's earth.knowlschool, N-U-L-L school.net. It's a really fun thing to play with. Okay. Why doesn't the current state currently do the more limit water use? Don't know that one. El Nino, La Nina, good question. So I had to skip over that part. The question is, how does El Nino, La Nina affect our precipitation? So back when I was talking about, let me change over here. Back when I was talking about how, oops, you don't want to see me again. There we go. When I was talking about that, let me go here. That often what we've noticed is that dry winters are sometimes followed by wet summers, right? For my example, that the mountain that's producing the heat, if it's a dry winter, then the soil warms up faster in the summer, all that whole story. So El Nino comes into that. So when we have an El Nino, we usually have above average winter precipitation, which then usually leads to a below average monsoon season. Other than that, there's not much of a correlation with El Nino, La Nina, and the monsoon. That was a good question. Let me see, what else do I have here? Let me see the situation. Okay, so I think the question is about what, not sure what that question is. Four Corners High is near low, coming in from the Gulf of Mexico. They reinforce or drive each other. So I don't know if this will help or not, but if I, let's go here. If I go to my, okay. So this is what the air temperature looks like at, this is the 700 millibar, so about 10,000 feet above the ground. And the weird thing is, even though everybody understands it's warm at the equator and cold at the poles, the really weird thing is that it's actually, the air temperature hardly changes at all until you get up close to near the pole, and all of a sudden you hit this blob of cold air. And this blob of cold air has these wiggles in it. These are called Rosby waves, and they change day to day. The position of these waves determines the jet stream, and the position of the jet stream determines where that four corners high is going to be. And so, back to my blurb about climate change, we think that what's happening is as you warm the continent, you're controlling where these Rosby waves tend to form, which controls where the jet stream goes, which controls where the four corners high ends up being. So that's the idea. What else do I have? All right, well, I think we are done here, guys. I appreciate you all joining in. This concludes the last of the Earth Week talks. Thank you for joining. Like I said, we will post the recordings later today. So thanks again to Katie for organizing all this. Thanks for Terry for coming in here and talking about rocks. And my name is Mel Strong. Thanks for listening.